RC networks as high-pass and low-pass filters. High-pass filters give you a pulse generator. Low-pass filters bring you back down to a sine wave. That's what we want today. So I'm going to use my oscilloscope's function generator to create a basic square wave, just because there's only so much room on my breadboard and I keep switching around the circuits. Once I move everything to a PCB, it'll be much more compact and I can fit everything together. So we'll have the oscillator feeding into the H-bridge, feeding into the RC networks, feeding into the amplifier. But for now, I'm only trying to demonstrate the filtering step. So let me show you the test circuit I have. I will have the function generator. First of all, because my oscilloscope is quite expensive, just to be careful, I'll put a safety resistor in. I won't need this in the final circuit, where the worst I do is blow a regular transistor. Of course, we'll have our ground on the other end. Our reference voltage, since this is a signal, the ground, the negative, the zero is the reference voltage for the whole thing. And then I will be using potentiometers as variable resistors, because recall, an RC network's timing, how long it takes to charge and discharge for the capacitor, is based on the resistance times the capacitance. And it's very easy to have a variable resistor, not as easy to have a variable capacitor. So I'll be choosing a capacitor and adjusting the resistor to get the effect I want. So I will have 3 filters, and I'll explain as I go why that number. 3 capacitors, that is our network. All of the capacitors, of course, connect down through the ground, and these are junctions naturally. One there, and one there. So the power will connect all the way through here, and it will continue to get filtered by the capacitors. So just for the moment, only look at this resistor and this capacitor as one RC network. So we have our input signal, and recall that an RC network is a resistor and a capacitor in series. For a low-pass filter, we have the resistor first. If there's only one filter, it doesn't matter, but we have more than one, so it does. So we have the resistor first, and then the capacitor, and the output is taken across the capacitor from one end to the other. The other will always be the reference voltage. The high-pass filter would be the capacitor here, and the resistor here, and we would take the voltage across the resistor. But we have resistor-capacitor. Now, why do I have different resistors? Isn't this all just one series resistance? Well, no. This capacitor, the loop, is like this. It doesn't involve these 2 resistors. So it's this plus this is the R, and that's the C. For this capacitor, it's this plus this series resistance, R times C, and it's all 4 together times this C for the third RC network. So, you know, the earlier ones are included in the later ones, but there's always one resistor that is only affecting the capacitor at particular points. So from here, we have this one we can adjust, and then this one, both of these are dependent upon this one, but only this one will adjust this one, and then when we move to the third one, both of these are doing both of these, but then we have a third one we can adjust for this. So we adjust it in stages. We'll connect only this one. We won't even have these connected. We'll adjust this, then we'll connect this one, so this stays the same. We don't mess with it, and then we adjust only this one to set the second filter, then connect the third filter, adjust the third one. So it's a bit more of a pain to configure initially, but we need that configurability. Again, I'll show you why when I'm using actual values. Now, the output, of course, will be here. If we had one filter, the output would be here, and then ground. The second, the output would be here, but you can see instead of it being an output, it's into the next RC network. So the true output will be here, plus ground. So this point and this point will be our result signal. And that's as simple as it is. No other trickery. I'm going to be physically swapping these capacitors and then just using my screwdriver to adjust these essentially trim pots. Since they don't have knobs on them, it's just a little trim pot. So let's get that oscilloscope on and get going. Right now, I'm going to make a statement. I will go into more detail in my upcoming amplifier video as part of this project, but right now the statement is simply that a capacitor, its filtering, as in what frequencies it filters more and less, is dependent upon its capacitance. A 100 nanofarad, 10 nanofarad, 1 nanofarad capacitor will all have different curves of how much they affect different frequencies of signal. So this is why I'm going to be trying different capacitors. So the first thing I'll do is turn on my wave generator. This is a square wave at 60 Hertz, 5 volts peak to peak, which, as I have said, I was getting wrong before, but now I'm getting right. It's 5 volts from the bottom to the top. So the center would be 0, and then this would be 2.5 volts, and this would be 2.5 volts. So 5 total from peak to peak, which I should have figured out, but I didn't. Anyway, so I have it connected to the safety resistor, and right now, the yellow waveform is measuring, if I can see where I put my probe. Let me move it over here to the actual input. So, of course, I had nothing plugged in, so this is the same thing, but it's a square wave. You should be able to see the square wave going up and down. And the reason I chose 60 hertz is I'm trying to mimic wall power, not the voltage of wall power, but the general shape of it. Close enough anyway. So the potentiometers I am using are 500,000 ohms. I have 3 of them, and I will begin with 100 nanofarad ceramic capacitors, which are the largest ceramic capacitors I have. Now, I did try electrolytics, even though in this circuit you shouldn't be using electrolytics because you've got the power going back and forth. It's fast enough, it should be safe, but, you really shouldn't be relying on luck and reoxidation. You should really not operate electrolytic capacitors like that. But as it turns out, the higher value capacitor actually didn't work as well. The large ceramic capacitor worked great. So luckily, I don't have to think about that. So I'm going to use 3 100 nanofarad ceramic capacitors in a row. But first, I will put in just one of them. So I will switch my signal view here to be the output of the RC network, which is the not ground side of the capacitor. And you see basically nothing, maybe a little wiggle, because I have a very large resistor across it. So I'm going to turn down the 500,000 ohms slowly, and you will see a signal begin to emerge more clearly. Once I get down low enough, see it's getting a little taller. There we are. That right there is a nice triangle wave, but it's very low voltage. So I had a 2.5 to minus 2.5 waveform. I guess I'll say 5 peak to peak just to be simple. And now, so this is 0.5, this is minus 0.5, so now it's a 1 volt peak to peak. That's terrible. We don't want to start filtering and losing the entire signal, so I'll keep turning this down. So if I turn it all the way down, we just get our signal because the capacitor is having very little effect. So if I very slowly, very gently turn up this capacitor, and let's zoom in a little so we can see the waves. If I slowly, gently turn up this capacitor, we see the first thing that happens is it begins to smooth out the corners, since it is a low-pass filter. If I get it just right, this is a large resistor, about like this, maybe a tiny bit more. There it is. That right there. If you recall my RC network video, I showed you a waveform roughly like this, where it's approximately 1 tau going up and 1 tau going down. Not exactly, I'm just eyeballing it here. But very roughly, I'm letting the capacitor charge and then discharge about its time constant. And as you can see, as I filter the signal down and change the shape, it loses its voltage. So since I want 3 filters, I'm going to say, let's do about half a volt, right? I don't want to go overboard. We're going to have multiple stage filters here. Because if you want your triangle wave, you can just turn the resistor way up and the timing will get you a triangle wave. But I can get one while retaining more voltage by using an extra stage. So this is at about 2.5, so I'm going to go down to about 2 on the peak. I'll turn up this resistor to about there. And so now we have definitely something spiky. It's more like a ocean wave kind of thing, stylized one. But you can see it has smoothed out the edges. So now, that's the first stage. So what if I put in another 100 nanofarad capacitor? Now watch, you might notice a very small change when I plug that in. It has a slight effect on the first signal, but not too much. But I will actually measure the second signal now. And now, of course, there's no signal because we have 500,000 ohms. If I turn the second potentiometer down to 0, we get our original waveform pretty much. So this is why I'm adjusting one at a time. I get the first one where I want it, and the second one roughly. But if we notice, we've actually lost a little voltage, partly because I bumped this. So I'm actually going to turn the first one back up a little bit because the second potentiometer is at 0. So essentially it's not there. And I'm just adjusting this again. So let me get some of my voltage back. That'll about do. Now I will turn the second potentiometer up from 0. And we get a triangle wave with much less resistance than I did before. If I turn it up to here, we've lost about as much voltage as we did before, but now it's more rounded. It may be hard to tell do take my word for it. I've looked at these waveforms back and forth. These peaks are more rounded, smoother. But I, again, don't want to lose that much voltage. So I'm going to say, let's lose only another half a volt on the top and bottom. So you can see it's still curvy, but it's much more triangularly. Let's try a third one. A third 100 nanofarad capacitor. Plugging it in affects the circuit very little. Switching the signal to the third and final RC network, no signal naturally. Turn down the resistor, potentiometer, and you can see once again we have lost a little voltage, so I'm actually going to turn this second potentiometer back up. In fact, I'm going to turn all of them to 0, so we get back our original signal. But do you see it's a little curved? I have all 3 potentiometers at 0 now, and we have a very slight rounding of the score wave. That's because of my safety resistor. Recall, I have a 1000 ohm, I didn't say the value, but I have a 1000 ohm resistor right there that the signal is going through before it reaches any of the potentiometers or capacitors. And that is effectively an RC network. Very slight one, but that's an RC network. Because right now, if I had all these potentiometers to 0, this would be a roughly short circuit, and I don't want that. So with these to 0, I will now turn up the first one to lose my half volt, about there. About, let's say, there. Once again, I'm using a very large potentiometer. Let's do that. Now the second one, I will turn up to lose about another half a volt. Gently, gently, super gently. All right, now the third one. So we're back to where we were. Now I will engage the third filter. And once again, if I turn it to here, we've lost the voltage that we did in the very first place to get the triangle wave, but now it is much, much, much smoother. Can you see that? It's much smoother. But let me turn this down and lose only half a volt. So now, instead of having a 0.5 to 0.5, so 1 volt peak to peak, I have a 2 volt peak to peak, minus 1 to 1. But this is with 3 capacitors of the same size. Recall how I said the frequency response is a little different depending on the capacitance? So remember this rough-looking waveform. Let me turn all the potentiometers back down to 0. Let me switch the signal back to the first one, and I'm going to do a little swap. So there's our rough first signal. So I will take out capacitors 2 and 3. So capacitor 1 is a 100 nanofarad capacitor. Capacitor 2, the second in line, will now be a 10 nanofarad capacitor. And the third capacitor in line, the final filter, will be a 1 nanofarad capacitor. So a 100, a 10, and a 1. Now let's do the same thing we just did. But actually, I am going to switch my signal to the third one because I can adjust them separately by having the potentiometers at 0. So we have our nice square wave here, 5 volt peak to peak. So if I turn up the first potentiometer, the same thing as last time will happen. If I lose about half a volt, we'll get same wave we did. Now, I will turn up the second potentiometer with the 10 nanofarad capacitor, and it will look very similar, but if you're able to see my screwdriver, I was able to turn the screwdriver much further before the signal started visibly going down. Recall, its resistance times capacitance is your tau constant. 100 nanofarad is 10 times bigger than a 10 nanofarad. So because the capacitance is smaller, you need a bigger resistance to get the same time constant. So I've gone down about half a volt again, and already at this moment, this is smoother than the second filter last time. It's hard to see. Like I said, I've been staring at these waveforms multiple times, but with only the second filter, in the last one, it was still pretty sharp and pretty angular, definitely smoothing, but still pretty angular. This one is already very close to the sine wave we want. So now I will turn up the third filter, the 1 nanofarad capacitor, and I'm turning this screwdriver a lot. And when we get down to our 1 volt peak to peak, roughly, look at that. It's not perfect, but it is very close. Much smoother than last time. Let me not hit my screwdriver on my screen, please. It's not a huge dramatic thing. They're very close to each other, but this is in fact smoother. But the fun thing is this 500,000 ohm potentiometer is at max. It's at 500,000 ohms. 0 to 500,000, because the 1 nanofarad is 100 times smaller than the 100. So you could, of course, power down your circuit and use a multimeter to measure these potentiometers to see which actual resistors to put in if you had an exact signal. And you might say, you have over 500,000 ohms going on here. Isn't that going to destroy your ability to do anything with the signal? That's why I'm putting in an amplifier. This stage is to smooth the square into the sine. The oscillator produces the square. The oscillator feeds the H bridge, which changes a 0 to positive square to a negative to positive square, and then I take the negative to positive square, which is effectively what my function generator is outputting right now, and I'm going to filter the square into this sine wave. And then the final stage is to feed the amplifier, which is just a transistor and a couple resistors, nothing grandiose here, just a regular class A, to use the shape of this signal to actually generate a full voltage sine wave. And if I'm doing that, then this being high resistance, very little current able to flow through all of these resistors is fine. Because number one, the transistor amplifies. The transistor base needs a small signal, and then it amplifies. That's why it's called an amplifier. But second, it's more energy efficient. Now, the whole thing is energy inefficient. We're doing this for fun. But the point is, think about what's going on when you use a resistance. Is high resistance actually a problem? Sometimes no. Sometimes yes, sometimes no. It depends entirely upon the situation. In this case, because we're feeding into an amplifier, we don't care. So I can use more resistance to get a better shape with the same number of components. And there you go. Now, one question you might be asking, and before that question, like I said, the difference this makes is noticeable, but it's not major. I'm going to do it because I want that little bit more smoothness, but we got a plenty smooth wave. We got a sine wave. We got a kind of rough cut sine wave, but we got a sine wave with just the 3 bigger ones and less resistance, but I'm going to do the better one. What if these are in the reverse order? What if I have the 1 nanofarad, then the 10, then the 100? The 100 nanofarad being the final filter. Let's do a quick demonstration. So I will now turn up, all of the potentiometers are at 0. I will turn up the first potentiometer, which is connected to the 1 nanofarad capacitor. As we can see, roughly does its job. Now I will turn up the second one, now that we have about a 0.5 volt drop from the peak. Turn up the second filter on the 10 nanofarad, and then the third filter on the 100 nanofarad. And there is the same roughly 2 volt peak to peak, minus 1 to 1, that we had a minute ago. But hopefully you can clearly see this is not smooth at all. This is straight up a triangle wave. And I'm using less resistance too. The first potentiometer connected to the 1 nanofarad capacitor, I barely turned up at all. In fact, I turned it up about as much, roughly speaking, as I did when these were reversed. But when I had the 1 nanofarad capacitor in the third position, I turned it all the way up to 500,000 ohms. But if I had turned it up any more, I would have lost too much voltage. So by the time I turn these up so that I get the voltage I want, we've barely smoothed it all. So if you're trying to low-pass filter, you always want to go from biggest to smallest. And looking at a spec sheet for these capacitors, or any similar capacitors, would probably give you a response curve of frequency versus resistance, effective series resistance for a capacitor. So you could see from that which frequencies you're likely going to filter out. I just realized my hand is fuzzy when I do that. But in short, it doesn't work. So let me put them back the original way. So it is less resistance. So let's just count. 1, 2, 3, 4, 5. 5 notches on my screwdriver is the full rotation of this potentiometer. So to get the curve where I want it, I do 1. That's 1. 2, the signal is already degenerate. So I have to do less than 1 notch for the first filter. Let's do 1. Once again, the signal is already almost gone, so it's less than 1. And this third one, once again, less than 1. So much less resistance. Much less resistance. In fact, similar for all 3, just to get down to the crappy triangle wave. But if I switch them back to where I had them, first the 100 nanofarad, then the 10, and then the 1. So now let's count. 1, and it brings it way down. So the first one, the 100 nanofarad, I need very little. Lose half a volt on the peak. The second one, 1, and that's close to right. Maybe 3/4 of 1, 5/6 of 1. And then the third filter we already know, all the way up. It's almost exponential. So barely any for the first one, maybe 3/4 or nearly 1 for the second one, and all 5 notches on the screwdriver for the third. And we get our nice 2 volt peak to peak smooth wave. So if you want a nice sine wave, you start with a bigger filter, then go to a smaller and a smaller. And just for fun, before I turn everything off, I'm going to plug in my other probe so we can simultaneously see the actual input square wave compared to this and get an idea of what we're losing. Now, I don't technically need this ground plug as much because the function generator is grounding it, but let's do things right. So I'll just plug this straight into the input with no filtering at all. Turn on the green, and then just fix the signal so it's nice and centered, and there we go. Make it a little taller so we can see it. Now, here's an interesting thing. Remember the charging and discharging cycle? The yellow is after all the filters. The green is before the filters, the pure signal. So here is where the signal was low and goes to high. The capacitors were outputting low, and when the square wave switches high and feeds the capacitors, they're charging. And then when it switches low, here, they start discharging. So through all three capacitors, unsurprisingly, the frequency is preserved of the core wave, but we're filtering out all of the sharpness. But as I said, we're losing voltage. The yellow one is on a 500 millivolt scale. The green one, the input signal, is on a 1 volt scale. If I put them on the same scale, this is the voltage we've lost. Unnecessary evil, but we can put it into an amplifier. In fact, the amplifier doesn't really need very much voltage at all, certainly not a 2 volt peak to peak. So we could even turn these up just a smidgen more if we want. Not too terribly much now, but I could actually turn these up just a smidgen more. Not that one. I'd need more than 500,000. But if I do a little more filtering, we get an even smoother wave, and that's perfectly fine. This is only a 60 hertz signal. So, as you might remember, higher resistance means a slower response when the voltage changes. But at 60 hertz, you would probably need tera ohms to really have a detrimental effect on the delay. Electricity may not go at the speed of light, but it goes pretty darn close. If we were working with gigahertz signals or even megahertz signals, this resistance might start to affect it. But at 60, not a bit. So I can get myself as smooth a wave as I want right into that amplifier. And we're done. So that's how you chain your low-pass filters to get a nice sine wave out of any other wave. Remember the Fourier series, the more filters you have, the more high frequencies are filtered out. So with an unlimited number of capacitors and resistors, you could eventually take any signal whatsoever other than DC and get a sine wave out of it of some kind. Get yourself down to nothing but that core base wave. But fortunately here, we need only 3. And you could do it with 2. But for me, 3 is a lot easier to adjust. It's a lot less fiddly. So 2 or 3 capacitors, 2 or 3 resistors, and square becomes sine. So the next task is going to be to make it bigger, because we don't want to have a 9 volt input and get a 1.5 volt output. That would be just lame. Until then, be seeing you.